This is number 9 from the Honors Conceptual Physics Practice Newton's Law of Universal Gravitation worksheet. It's a question about the gravitational force between these two objects, and there is a gravitational force between these two objects. One object being the planet, the other object being the spacecraft. And even though the planet is so much bigger than the spacecraft, we know that whatever pull the spacecraft experiences, there's also an equal but opposite pull on the planet. So I can do congruency slashes here and here. There's an equal and opposite pull between those two. But what we're really going to focus on is the distances between these. We're really interested in these distances because this is basically a plug-in, but the challenge of this problem is determining what the distances are. And one distance that I have to be concerned about, and first it's worth saying, we measure gravitationally from center to center. So we're interested in the center of one object to the center of the other object. And the first distance I'm concerned with is this distance here, which goes from the center of the planet to the edge. Then the next distance is from the edge of the planet out to that object. This I'll call capital R for the radius of the planet. This I'll call d as the distance from the planet. And ultimately what I'm going to do is plug into this equation f sub g is equal to capital G m1 m2 over r squared. So the real trick here is I need to find r. I need to figure out what r is. Well, r is equal to that radius plus the distance. And don't be intimidated by the letters. I'm just going to get two numbers and I'm going to add them up. The radius of the planet, looking at the table, is half of the diameter, and it needs to be in meters. So first, can somebody tell me what is the diameter of the planet in meters off your table? Well, actually, I have it right here. I'll say it out loud. It's Neptune. I'm looking it up on the table. It's 49528, but I'm going to write that down. That was in kilometers, so I'm writing it down in meters, and I'm multiplying by 1,000. But I need to divide that by 2. And that works out to be, for the radius of the planet. Okay, so that radius of the planet works out to be something. The distance of the planet above the surface. We are told in the problem that the distance of the planet above the surface is 4.6 times 10 to the 6 kilometers. So 4.6 times 10 to the 6 kilometers, I'm going to write that down as 4,600,000. That's in kilometers. But watch this. I'm adding 3 more zeros to make it into meters. All this work just to get the distance, right? It's just basic math to get the distance. And that number works out to be 764. Okay. So I've got my 2, I've got my R, and I've got my D, right? I've got these two numbers, and I'm just going to add up these two numbers now to get my overall R, and I'm going to pause this and do a bunch of shrinking and moving. So I clean this up a little bit. So when you add up those two numbers, you get 4,624,764,000 meters. That number goes into the equation for R, but you have to square it. So now it becomes a calculator problem, and unfortunately I can't tell you how to enter this on your individual calculator, but we now know R. We know G, it's 6.67 times 10 to the negative 11th, and that's a constant which is on the board, and I'll write that in a second. We know the mass, and you put all those numbers in on your calculator, and you get the force, which I think ended up being, was it 0.707? 0.707 newtons.